Okay, we're going to talk about Gibbs free energy and how we relate that to equilibrium. So the question that I've got is A goes to B compared to A is in equilibrium with B. And how can we quantify this in terms of the thermodynamic potentials that we have learned thus far? Okay, so you have A going from pure A to pure B. So if this is a time domain, and so you start and then you end here, that would represent this first A goes completely to B. But hopefully by now you know that it's very rarely this is the case. Typically this is the case to where you've got somewhere in between pure A and pure B is where equilibrium will find, where you will find equilibrium. So instead of saying this is like a time domain, let's call this a reaction progress coordinate. And so we call this then the extent of reaction, and we give it this symbol, the little C type symbol. And it's like a little backwards E, or not backwards E, a backwards 3 with a hat and a tail. Hat, backwards 3, tail. Go team. We also call it squiggle. Anyway, so here we've got the change in the number of moles of A going from initial extent of reaction to at some point throughout the reaction is going to be less than 0 for a loss of A. Oops. And it's going to be greater than 0 for a gain of A. So I should say B. There we go. So we're losing A as we go forward in the reaction, and we're gaining B as we go forward in the reaction. And so that forward, then that parameter we can call the C value, which is the extent of the reaction. So D in A, that's kind of funny. So the change in the number of moles of A is equal to minus the change in the extent of the reaction. And likewise, the change in the number of moles of B is equal to positive the extent of the reaction. Because as you go forward along this line, anything that you lose in A, you are going to gain in B. Okay, so you can then denote the change, the reduction in the reaction progress is equal to the gain in the reaction progress in terms of with respect to A or with respect to B. Sound good? Okay. So now we're going to define equilibrium then. So define equilibrium, just going to throw in some random letters there. Equilibrium as delta G of R, of the reaction, is equal to the change in the Gibbs energy with respect to the extent of the reaction. Okay? And that is going to equal 0 when we're no longer changing the extent of the reaction. Therefore, delta G of the reaction is equal to 0. Okay, I'm going to change to a different plot so you can better visualize this idea. Okay, so I've got G, absolute value G, or the magnitude of G with respect to the extent of the reaction. So if I have a curve that looks something like this, you might say, oh, well, it's clear that equilibrium is going to occur where delta G is equal to 0 at the bottom of the hill. So at this point, we've got delta G equals 0. So 0 at equilibrium, okay? But, and so I'll go ahead and make a line right there. So this designates the equilibrium condition. If, however, I'm right here, the tangent this, delta G is going to be less than 0. So you've got a negative delta G. So if it's less than 0, we've got a spontaneous reaction. Okay, the reaction will continue until it reaches equilibrium, which means at an early extent of the reaction, we are still maintaining a negative delta G. Therefore, we are going to continue to go towards until we reach delta G is equal to 0. And likewise, if we're over here, so this delta G is going to be greater than 0. So notice that it's positive. So greater than 0 means spontaneous in other direction. you've probably been okay with talking about the directionality of a reaction, but what does that mean? It's not it's not movement, you know, one way or another, but it's in the direction of the extent of the reaction. So when you've said that there's a directionality with reactions, you've always been actually talking about the extent of the reaction. So it's spontaneous in the other direction, which means towards a negative extent of reaction, going back the other way along this coordinate. So we then define delta G of the reaction is equal to the change in G with the change in the extent of the reaction at constant P and T. And so because we've got delta G of the reaction is equal to the change in the Gibbs with respect to the extent, we can then define, or sorry, because we've got this, and then we've got delta partial G partial N B is equal to mu B. Again, this is the chemical potential. We can then say that mu, oops, mu A is equal to mu B at equilibrium in this particular case. And so from here, we've got delta G, so this is the change in the Gibbs energy at any particular point, can be then related to the chemical potential of A or the chemical potential of B, which is then related to the extent of the reaction. Cool? And so along these curves, you're going to have a more negative delta G here than you will have here, which means the chemical work you can get, the chemical potential that you can extract from this reaction is going to be greater at the initial stages of this reaction and less as you approach equilibrium. So there's going to be a reduction in the chemical potential as you get closer to equilibrium. Cool. Okay. So we define then, so relate to the chemical potential of A and B, which is the, let's define it. So the chemical potential is the potential for chemical change. The likelihood that we can change the system, and that likelihood of change decreases as we get to equilibrium.